In the autumn of 1944, the south of England was introduced to a terrifying new weapon, known locally as the Flying Gasworks. The rest of the nation called it the V-2, but in its German birthplace it was the A4 rocket. Fired from ordinary city streets and quiet wooded avenues in Holland, these projectiles struck London with zero warning. Striking the ground at nearly 3,000 miles an hour, the A4 traveled its maximum 200-mile range in just 5 minutes. Following the war, British forces initiated a massive effort to understand this revolutionary technology. At Cuxhaven, under British supervision, captured German technicians reassembled and launched these ballistic leviathans. We are looking back at the intense logistical ballet of liquid oxygen, hydrogen peroxide, and volatile alcohol that powered the dawn of the space age. Witness the assembly, the fueling, and the raw power of the A4 as it paved the way for modern rocketry.
In the south of England in 1944, you know this as the Flying Gasworks. In the rest of Britain, it was known as V-2. But in Germany, the land of its birth, it was called the A4 rocket. And on the evening of the 8th of September 1944, the first A4 landed in London. More than 1,000 rockets were aimed at London, and most of them were launched from The Hague in Holland. Not far from the historic Palace of Peace, right in the center of The Hague, was an ordinary city street. This street was cleared of traffic and pedestrians for a couple of hours, and then a rocket was ready for launching. This is an actual launching site used by the Germans. You will see how little special preparation they required for firing a rocket. They wanted protection from the RAF and from the wind. The rocket was always placed on a launching table, in this case in the middle of the avenue of trees. These trees are just about the same height as a rocket on a launching table, so conditions were pretty good. This should prove to you that a rocket can be launched from almost anywhere. An area 23 feet square is sufficient, provided it can be approached by vehicles. The Germans fired from town or country. Along this avenue, there were 9 separate launching sites. A wood is the ideal site for rocket launching, as long as you can get in and out of it easily. Aiming marks were painted on trees, and a pit was dug for the firing control vehicle. The firing troop commander was in this vehicle about 30 yards away from the actual launching site. In a wood, the ground has to be leveled, and you must put down a firm base to support the launching table and the rocket. The Germans used wood or steel sleepers to provide this base. The Germans fired their last rocket against Britain in March 1945, and we took over after that. We collected damaged rockets from all over Germany and decided that the German scientists and technicians would fire some more rockets, but this time under British control. Much of the rocket equipment had been blown up by the retreating Germans. We had to reassemble it, find out how it worked, and make new equipment for ourselves. A thing like this had to be turned into a workable launching table. We reconstructed equipment, we made new vehicles, and we finished by making complete rockets from captured equipment. Sometimes luck was on our side, as when we found a factory in the British zone which was producing road transporters for the local farmers. These road transporters, known as Wiedelwagens to the Germans, are used for carrying the rocket, so the factory started to make them for us. Among the vehicles we reconstructed was this one, used by the Germans to convey liquid oxygen from the railhead to the launching site. At Cuxhaven, we took over a gun testing range and put up some new buildings such as this proofing tower where the rocket stood while undergoing some of its tests. Very soon we had our own repair plants at work, where we assembled rockets from captured German equipment. Besides shelters for rocket parts, we built workshops, sheds, and stores. We captured a large number of German components, aluminium tanks for alcohol and liquid oxygen, and cylindrical drums containing rocket warheads. The tanks for holding alcohol and liquid oxygen are extremely light, although they're so large. The capacity of one of these tanks is approximately 4.5 tons of liquid oxygen. Yet 4 men can carry an empty oxygen tank without any difficulty. The mechanism of the rocket is best studied in diagram. The rocket is driven by the reaction of a jet of high-speed gases. This jet of gases is produced in the venturi or combustion chamber in the rocket by the combustion of alcohol and liquid oxygen. Here is an actual combustion chamber. It is made of steel. The pressure in the venturi is very high during burning, and to force the fuels in, the rocket has 2 pumps, one for each fuel. These pumps are driven by a turbine placed between them. This turbine develops 600 horsepower, since 8.5 tons of fuel have to be pumped into the combustion chamber in the space of 60 seconds. Here is the complete unit, turbine and 2 pumps. The turbine is driven by steam, which is produced by the chemical reaction between hydrogen peroxide and sodium permanganate, contained in these 2 tanks. Forward of the tail unit are the 2 fuel tanks. First, the liquid oxygen tank, then the alcohol tank. Here they are during the assembly of an actual rocket. Owing to the shape of the rocket, the alcohol delivery pipe has to pass through the center of the liquid oxygen tank. Finally, in the front of the rocket, we have the control compartment and the warhead. In the control compartment are 2 gyroscopes. These gyroscopes are the brains of the rocket. They are in universal mountings. Electrical pickups measure the movements of the gyroscope and translate these movements to the carbon vanes and the trimmers in the tail unit. These vanes and trimmers direct the rocket, both in bearing and elevation, along its trajectory and prevent any deviation from its planned course. The 4 vanes are in the jet of the rocket, and there is a trimmer on each of the 4 fins. This mock-up represents the inside of the control compartment in the rocket. In the background is a skeleton tail unit, with the vanes and trimmers in position. As the control compartment moves, the gyroscopes move in their mountings, and these movements are conveyed through electric cables in the rocket to corresponding servo motors in the tail unit. There is a servo motor for each carbon vane and trimmer. The servo motors move the vanes and the trimmers to counteract the original movement of the control compartment and to keep the rocket on its course. This gyroscope controls the elevation of the rocket by moving a pair of the carbon vanes, thus turning the rocket from the vertical over to an angle of 43 degrees. The other gyroscope controls the direction of the rocket by the movement of this pair of vanes. These 4 vanes, made of carbon to resist the heat, are situated in the jet, and they can control the rocket only while the jet is burning. This period of control lasts for 60 to 70 seconds, and covers the first 20 miles of the trajectory up to the all-burnt position. When it has reached the all-burnt position, the rocket is a free projectile, just like any artillery shell after it has left the muzzle of the gun. This is what actually happened when the Germans fired on London from The Hague. The distance is nearly 200 miles, the maximum range of the A4. The rocket was controlled for the first 20 miles of its flight, or until the jet had stopped burning. At this point, its velocity is 6,500 feet per second, and it is at 43 degrees angle of elevation. It keeps on climbing until it has reached a height of 50 miles, which is halfway on its journey. Then, still traveling towards London, it starts to fall. But it is slowed up to a velocity of 4,000 feet per second by the resistance of the air. It actually strikes the target at 4,000 feet per second, or nearly 3,000 miles an hour. The whole journey takes only 5 minutes. By comparison, a 16-inch gun will fire a 1-ton shell about 25 miles. The highest altitude that man has yet reached is about 12.5 miles, accomplished by 2 Americans in 1933. In the workshop which we built at Cuxhaven, German technicians and engineers under British supervision built rockets from the parts we had collected. Here are A4 rockets in various stages of construction. First of all, there are the 2 fuel tanks, one for liquid oxygen and one for alcohol. They are in a half shell padded with glass wool. This rocket has the motor attached to the tank compartment, which is now complete. The other half shell has been added. But the control compartment is not on the rocket yet. Now we see a tail unit ready to be added to the rocket. Wiring is being connected so that the rocket can be tested for electrical continuity. The control compartment has been fitted to this rocket. There's a complete rocket. It was painted black and white so that we could see it more easily when it was fired. Now the rocket, to be tested, is connected to a compressed air line. The tanks and pipes are tested for leaks by air pressure, and at the same time, all the electrical circuits are checked for continuity. When the tests are completed, the tail unit is added to the rocket. At the other end, the warhead is secured. This wasn't the normal German practice at this stage, but we wanted the warhead on the rocket so that we could lift it into the proofing tower. Then the rocket was lifted from the assembly line onto a transporter. It was then taken to the proofing tower so that the control apparatus could be adjusted. The rocket was placed in the vertical or launching position in the proofing tower. The gyroscopes and the control units were inserted, and the steering tests were done. To do this, the axes of the gyroscopes were lined up with the axis of the rocket. When the tests were completed, the rocket was ready for firing. We transferred it directly onto an elevator transporter known as the Meillerwagen to the Germans. When this stage was reached in wartime, the Germans used what they called the hot cakes method. They put the newly tested rockets onto a train and sent them straight to the railhead in the firing area. The Germans almost always fired a rocket within 3 days of its production, because they found that the number of failures was seriously increased by long storage. Now we are going to follow the operational procedure used by the Germans, starting at the railhead. At the railhead, the rockets were taken over by the technical troop of the rocket regiment. The German railway wagons were not long enough to carry a rocket, so the system was to load 2 rockets onto 3 railway wagons. The rockets were loaded without the warheads, which were carried separately in the middle wagon. The first job the technical troop had to tackle was the lifting of the rocket from the railway wagon to the road transporter. The mobile crane is used to lift the A4. The railway wagon is pulled out from underneath the rocket, and then the road transporter is pulled into position. The crane swings the rocket across and lowers it onto the road transporter. The road gets to the field store of the technical troop. This was naturally selected for concealment and for its handiness to the firing sights. The railway engine shunts the wagons to bring the second rocket under the mobile crane, and the technical troop carried out the shifting process in the same way as before. In the German setup, there was 1 technical troop to 3 firing troops. Here you can see that the railway engine has brought the second rocket into position under the mobile crane, just as the first rocket leaves on a road transporter for the technical troops' field store. When the rockets arrived at the field store, the technical troops' first job was to fix the warheads on the new rockets. The warheads were delivered in their cylindrical transit drums. First of all, the transit drum is lifted by a small crane. The rocket warhead weighs about a ton, and it contains about 1,700 pounds of explosive. The drum is supported at the front while the warhead is screwed onto the control compartment. When the warhead has been fixed to the rocket, a man removes the securing bolt which attached the warhead to its transit drum. Then the drum is slid off. Once the warheads were fixed on the rockets, the technical troop's next job was to carry out electrical tests, make minor repairs, and hand over a 100% rocket to the firing troop. They used the mobile crane a great deal in this work, particularly in the transferring of the rocket from the road transporter to the Meillerwagen. Each technical troop had only 1 mobile crane on its war establishment, so that after use of the railhead, the crane had to be towed to the rocket store and set up there. The mobile crane was not specially designed for rocket work. It was a standard piece of German equipment, capable of lifting 10 tons, which is considerably more than the weight of the rocket before it's fueled. The crane could be towed behind an ordinary vehicle. A well-trained team could erect or dismantle the crane in about half an hour. Besides the testing and the delivery of the rockets, the technical troop were responsible for the transfer of fuel from rail tankers to road tankers. This transfer was done by a small petrol-driven pump fitted to the side of the railway wagon. The liquid oxygen was always brought to the firing area by rail. The actual transfer of the fuel was delayed to the last possible moment to avoid losses by evaporation. The fueling troop's road tanker holds only 6.5 tons of liquid oxygen, enough for 1 rocket, while the rail tanker contains 30 tons. Not only that, but the road tanker loses 3% of its contents by evaporation every day. The long pipe is put on to act as an outlet. When firing was ordered, the firing troop sent their Meillerwagen to the technical troop's field store to collect a rocket. This meant that members of the technical troop had to transfer the rocket from the road transporter to the firing troop's Meillerwagen. The transfer of rockets from technical troop to the firing troop could be done anywhere. It was not limited to the field store. In fact, the rocket was often transferred some distance away so that the storage site remained concealed, especially from the air. Before the transfer took place, the rocket was completed. The warhead had been fitted, and the electrical tests were satisfactory. The rocket on its road transporter is towed under one side of the crane. The firing troop tows their Meillerwagen under the other side of the crane. Then the rocket is lifted from the road transporter and transferred over to the Meillerwagen. The Meillerwagen supports the rocket in two places, with a clamp between the tank section and the tail unit of the rocket, and a clamp at the nose. The technical troop lowers the rocket into the two clamps. The forward clamp, which grips the warhead, is tightened up by a ratchet. Then the main clamp is screwed up. The lifting tackle is removed from the rocket. Now the empty road transporter is towed away. The firing troop takes over the Meillerwagen again. This elevator transporter is designed to have as much maneuverability as possible, and it can be towed at either end. The firing troop connects the Meillerwagen to its towing vehicle and takes the rocket off to the launching site. Meanwhile, the rest of the technical troop are completing the fuel transfer. The pipes connecting the pump to each of the oxygen tankers soon become covered in frost and snow because the liquid oxygen is so cold. That white vapor is not, of course, oxygen vapor, but water vapor condensed by the liquid oxygen. When the road tanker is full, the inlet valve is screwed down. The men wear special gloves to protect their hands against the cold. Now the technical troop's work is finished. By this time, the firing troop were working on the launching site. Once it was prepared, the first step was to tow the launching table onto the site. The requirements of a launching site are extremely simple. You need enough room to maneuver your fueling and firing vehicles, and a hard base for the launching table. At Cuxhaven, we had no operational problems, so we were able to build a concrete surface. If you remember the actual German sites we showed you, you will realize that an improvised surface is just as effective as a specially prepared one. Now the firing troop screwed down the legs of the launching table in order that these legs could take the weight of the platform. This was done so that the towing dolly could be removed. The launching table is placed over a surveyed mark on the launching site. This is done so that the rocket can be accurately orientated later on. The towing dolly was pulled out and wheeled away. The launching table has an adjustable jack on each leg so that the platform can be leveled. There's a turntable on the top for turning the rocket when it's standing on the platform. The launching table is made of welded steel and weighs 3,600 pounds. Between the legs of the platform, there is a flame deflector which splits the jet. The firing troop brought the rocket to the launching site on their Meillerwagen. They tow the rocket towards the launching table, but remove the towing vehicles while the Meillerwagen is still about 30 feet away from the table. In order to carry out adjustments and tests, when the rocket is in the vertical position, a cradle is put on the nose. This cradle is held in position until the rocket is erected by the front clamp of the Meillerwagen. The Germans move the Meillerwagen to the launching table by means of a winch. They can't use the towing vehicle to pull it, since the launching table is in the way, so they chose this winching method. The Meillerwagen is steered by hand into an exact position by the launching table. Once it is pulled right up to the table, the supporting jacks on the Meillerwagen are screwed down. Now the Meillerwagen is able to erect the rocket on the launching table. Although fueling would be easier with the rocket in the horizontal position, this wasn't done because of the light construction of the fuel tanks. These tanks are designed to stand the weight of the fuel only when the rocket is in the vertical position. In the horizontal position, the tanks would collapse. When the rocket is empty, it weighs 4 tons, including the warhead. But when it has been fueled, it weighs about 12.5 tons. The Meillerwagen arm is elevated by 2 hydraulic rams. The pressure for operating these rams is supplied by a small gasoline engine. This man is in control of the operation. The elevating arm of the Meillerwagen holds the rocket an inch or 2 above the launching table. Then the legs of the launching table are screwed up so that the table can take the weight of the rocket. The clamps on the Meillerwagen are released so that the rocket is standing without support on the launching table. The elevating arm of the Meillerwagen is lowered about 10 degrees. Then the jacks supporting the Meillerwagen are removed. This enables the Meillerwagen to be manhandled 90 centimeters, or about a yard, away from the launching table. Then the testing platforms can be fitted to the Meillerwagen at various heights. Meanwhile, the fueling troop were bringing up their fuel train. The train consisted of a towed alcohol bowser, a self-propelled alcohol bowser towing a trailer pump, then the towed liquid oxygen vehicle, and finally the bowser for T-stoff, or hydrogen peroxide. The fueling vehicles were concealed near the launching site until needed. At the launching site, the survey party now leveled the rocket. This was an initial leveling process to be checked at a later stage. The leveling was done by adjusting the legs of the launching table. The technicians of the firing troop removed the jet covers from the venturi. They also bolt the carbon vanes into position. These vanes were not put on earlier because they are easily broken. The air-operated valves in the fuel supply system are tested by using a mobile air compressor. This compressor is also used to fill compressed air bottles in the rocket. Paper covers, rather like paper drinking cups, are put over the oxygen jets. This is to make sure that the oxygen does not cause mechanical damage to the jets. When the preliminary tests were completed, the alcohol vehicles were called from their temporary parking place. Alcohol was always the first fuel to be filled in the rocket. The rocket is fired electrically from a control panel in a special vehicle. The electrical cables connecting the control panel to the rocket are supported on a long pole attached to the launching table. During the tests on the rocket, the batteries become exhausted, so they have to be replaced. When the alcohol fueling vehicles arrived, they parked along one side of the Meillerwagen. The outlet of the alcohol pump was connected to one of two permanent delivery pipes fitted to the elevating arm of the Meillerwagen. This delivery pipe extended the whole length of the Meillerwagen arm, and the alcohol was fed in through the control compartment to the top of the alcohol tank. Now the alcohol filling started. It took about 10 minutes to fill the alcohol tank in the rocket. The liquid oxygen trailer was the next fueling vehicle to arrive at the launching site. The Germans always tried to fuel the liquid oxygen within an hour of the time of firing the rocket, to avoid freezing up the valves. This arrangement of fueling vehicles round the Meillerwagen was a typical German layout. As well as the alcohol and oxygen vehicles on either side, the T-Stoff vehicle is directly in front of the rocket. The liquid oxygen is fed in at the middle of the rocket. The pump is connected to the permanent delivery pipe on the arm of the Meillerwagen. The sodium permanganate is the last fuel to go into the rocket, and at this stage it is placed in an electric heater to warm it up. The reaction between hydrogen peroxide and sodium permanganate, which produces the steam for the rocket turbine, is quickened if the sodium permanganate is warm. By now, the oxygen fueling is in full swing, and the pipes through which the liquid oxygen is traveling begin to show the characteristic formation of ice and snow. The oxygen fueling took about 8 minutes to complete. Now that the alcohol fueling of the rocket was finished, the pump was disconnected and the alcohol bowsers began to move off. During the oxygen fueling, the hydrogen peroxide is pumped into the steam unit. It is first pumped into a measuring tank fixed halfway up on the arm of the Meillerwagen. From this point, a measured quantity of hydrogen peroxide is run into the tank inside the rocket. Hydrogen peroxide is a corrosive fluid. The men who handled it wore rubber gloves, and the connecting joints of the pipes which carried the fluid were placed in buckets of water. Every now and then, the sodium permanganate, the other element used in producing the steam, was taken out of its electrical heater and shaken to mix it up and make it more effective. As the fuel tanks are filled, the weight of the rocket increases and the joint between the tank section and the tail unit needs retightening. An elevating ladder is used to get a member of the firing troop up to the joint. There is a danger that the coldness of the liquid oxygen might freeze up the rest of the machinery. So, to make certain this didn't happen, hot air was blown up through the rocket from an air blower. The Germans did this only if there was a hitch in the preparation and the rocket could not be fired within an hour of the oxygen fueling. As the job of each fueling vehicle was finished, it was driven away from the launching site. The oxygen fueling is almost completed, and clouds of condensed water vapor are pouring out. When the liquid oxygen tank has been filled, the connecting pipes are removed with the aid of a hammer. Once again, special gloves are worn for the operation. Just as the liquid oxygen fueling is finished, it is time to start the Z-Stoff fueling. The sodium permanganate is removed from the electrical heater and taken to the rocket. Now the sodium permanganate is lifted up the side and tipped into the tank through an opening in the tail unit. Next, the igniter is prepared. The wooden framework, which is fixed inside the venturi and supports the igniter, is put together. The igniter works like a large-sized Catherine wheel and is started electrically. Now that the fueling is finished, the arm of the Meillerwagen is lowered. The rocket is finally leveled and orientated in the direction of the line of fire. This is done by using a dial sight on the launching table, having as a reference a collimator set up over a trig point a few yards away. The trig point was established by preliminary survey. The igniter is placed in the venturi and connected up. Then the firing troop take cover in the slit trenches they've dug near the rocket. The troop commander goes to the firing control vehicle. The control panel from which the rocket is fired is in this vehicle. The final steering tests are made. And then the firing troop commander gives his orders.
Die Steuerung klar, ist klar. Das Triebwerk klar, ist klar. Schlüssel aufschießen. Schlüssel steht aufschießen. Durchschalten. Ist durchgeschaltet. Belüftung klar, Zündung klar, Vorstufe klar. Hauptstufe gegeben, Stecker gefallen.
When the rocket reaches an altitude of 40 to 50,000 feet, a vapor trail condenses in its wake, just like the trail made by high-flying aircraft. The effect of the rocket going down is an optical illusion caused by the angle of the camera which shot this scene. The rocket's still going up all right. Now we see the operation in slow motion. When the troop commander says durchhalten, the igniter is lit and the alcohol and liquid oxygen, which are flowing under gravity, are ignited. This gives a thrust of 8 tons, which of course won't lift a 12-ton rocket. The troop commander looks at the flame to see that it is burning evenly. When he sees that it is, he gives the command, Hauptstufe. This starts the pumps. The thrust from the jet increases rapidly up to 25 tons. The control cables are ejected electromagnetically and the rocket takes off. This is a close-up in slow motion of the rocket leaving the launching table. was the first operational model of a new conception, complicated to produce and not very accurate or reliable in action. But it was extremely difficult to counter. And to the Germans, its range of 200 miles was only a beginning. They were already thinking of a rocket that would cross the Atlantic and could be guided to a controlled landing by a pilot in a pressurized cabin. We cannot afford to be complacent about the rocket and its potentialities in the future. The record of this film is a warning that we've got a lot to think about.
What caused an air force that was in many ways vastly superior to the Allies to come crashing down? Is there a distinct turning point that made Germany's aerial arsenal impotent against the combined strength of Britain, America, and the Soviet Union? For the first time ever, put yourself right in the middle of the debate as we try to solve the greatest arguments in the history of aviation. What caused the Luftwaffe to fail? In 1933, Adolf Hitler becomes Chancellor of Germany and later the Führer, enacting complete control over the fatherland. Eager to reclaim the lost territories taken from Germany after the Treaty of Versailles, the Nazi war machine realizes early on that the formation of a strong air force is vital. In 1935, it becomes official on paper, and the Luftwaffe is born. The man put in charge of this department is Hermann Göring, a prominent ace from the Great War.
Goering was a World War I fighter pilot. He was not interested in technology. He said something at one point, he said, well, this device is a box with coils, and I don't like boxes with coils. He's still had this sort of, well, if you're courageous and brave, you don't have to worry about technological gizmos.
In building this new air force, the Nazis possess many advantages that other nations do not, including a first-class aircraft industry, symbolized by the names Messerschmitt, Dornier, Heinkel, Junkers, and Focke-Wulf. Brilliant engineers capable of taking aerodynamics to a whole new level, and a highly educated population that can build aircraft on a mass scale. By 1938, production rises to over 5,000 planes. 1 year later, that figure soars to over 8,000, a testament to the importance Nazis place on the doctrine of air power.
What the Germans were trying to do was to employ new machines, new technologies, but to employ them in the service of a very, very old way of war that had served them well in previous conflicts and they felt would continue to serve them well in the future. I think this sets the Germans somewhat apart from neighboring countries in the 1920s and 1930s in that they are not truly looking ahead as much as they are looking back to their old traditions and grafting new technologies onto them.
Before war is declared in August of 1939, Germany's aerial arsenal is impressive to say the least. Ready to go is the Me-109, a superior single-engine fighter, the Junkers 87 Stuka, a terrifying dive bomber, the Heinkel 111 and the Dornier 17 Flying Pencil, two top-of-the-line medium-range bombers. This, in addition to the largest air transport industry in the entire world, exemplified by the Junkers 52, a workhorse that will be at the centerpiece of the German offensive. Even with all these phenomenal aircraft, a key ingredient is missing, as is often noted by Second World War historians: the absence of strategic bombers. This void does not go unnoticed in 1935, when General Walter Wever, realizing their importance, enthusiastically supports the building of long-range aircraft to battle any potential enemy, most likely the Soviet Union.
General Walter Wever was promoting what he called the Urals bomber. He believed that the industrialization, tanks, planes, etc., that was going on in the Urals area had to be demolished if you were going to win a war against Russia.
Wever writes, "Air power carries the war right into the heart of enemy country from the moment war breaks out. It strikes at the very root of the enemy's fighting power and of the people's will to resist.
Yeah, Walter Weber was very much in favor of this long-distance bomber to try and bomb Russia. And that actual project was given the name of the Ural bomber. Weber actually then put specifications out to both Dornier and Junkers for the building of this long-range bomber. Out of this came the Dornier 19 and the Junkers 89. But neither of these aircraft had the performance that was currently available in the United States on the B-17 Flying Fortress. So therefore, neither of those airplanes really progressed very far beyond a couple of prototypes.
Dying due to a plane crash in 1936, his doctrine epitomized by the Dornier 19 and the Junkers 89 are scrapped by Goering.
Goering, I think, didn't go along with this because he rather took the view that Hitler had, that they could win by blitzkrieg, and they wouldn't be required to get into this lengthy process of using heavy bombers.
Inquiring as to how many twin-engine planes can be made for every four-engine one, the answer given to him is 2.5. The Field Marshal's response is that the Führer does not ask me how big my bombers are, but how many there are. It is important to note that the decision not to build long-range bombers cannot be considered a failure. For Germany, the raw materials needed to build such planes would require large amounts of rubber, metals, and fuel, all of which would have to be imported for a hefty price. Of the 4,500 tons of aluminium needed per month for aircraft production, only half is available during the Weber era. The Air Force that he and others envisioned was simply uneconomic at the time. What truly represented the German way of war is instead a tactical Air Force.
The German war of movement attempted to defeat as much of the enemy army as possible within the opening weeks of fighting. So the tactical level of fighting for an individual position, and then the operational level of attempting to defeat an enemy army. But arguably, Germany had never been very good, and this would go back to Prussia before it, at the kind of long-term strategic planning that the Allies were so skilled at in World War II. Arguably, this was because the Germans felt they had to win all their wars quickly or they would not win them at all, and that attempting to play strategic warfare with the vast economic and industrial resources of the United States was a losing game from the start.
Working closely with those on the ground, the Luftwaffe is wildly successful as the Second World War begins. Poland is easily demolished. Norway is taken away from the British effortlessly. The Low Countries and even the power of France cannot resist German might during the year 1940. It appears that nothing can stop Nazi forces from gobbling up the continent of Europe.
Certainly the Luftwaffe played an extremely important part in the opening German victories of World War II. And when we say opening victories, we don't mean the first 6 months, we mean the first 2 years, in which it looked like a German victory was very much in the offing. The German Air Force was very skilled at the tactical level, that is, cooperation with the ground forces. It was extremely successful at the operational level of war, the intermediate level, that is, carrying out campaigns against enemy supply lines, for example, feeding troops and men to the front.
With the fall of France, Britain is the only nation standing in the way of this German juggernaut. In order to finish off the rebellious island nation, a plan known as Operation Sea Lion is approved. It calls for the Luftwaffe to achieve air superiority over the English Channel. Once this is completed, German forces will be deployed onto British soil. However, during this pivotal battle, the Luftwaffe is dealt its very first aerial defeat. Primarily through the use of Spitfires and Hurricanes, the English are able to push back German planes from the coast of Britannia. While this monumental struggle ensues, we discover one of the Luftwaffe's greatest failure, its lack of coordination with the Kriegsmarine.
Goering said, everything that flies is mine, and bitterly fought against any attempts by the German Navy to get a hold of a piece of the air action. When they wanted long-range aircraft assigned to them, Goering, actually, Dönitz went behind Goering's back directly to Hitler, and I think got a dozen of the Focke-Wulf Condors assigned to him. Goering, when he found out about this, was furious and actually cut off all cooperation with the Kriegsmarine at this point.
Despite pleas by Admiral Raeder to create a separate air force for the Navy, Goering refuses to give the green light to any potential inter-service rival. The roots for this conflict come from each service's desire to be recognized as the one who brought victory to the fatherland.
Of course, there has always been the rivalry between the Navy and the Air Force from the point of view that we refer to ourselves as the Imperial Navy and refer to the Air Force as the Nazi Air Force. So that differentiated us already in attitude and character.
In hindsight, Goering's decision proves fatal as Germany and Britain battle it out in both the skies and on the high seas. Winston Churchill would write that the greatest threat to Britain was the Battle of the Atlantic, where German U-boat submarines are enormously successful in sinking English shipping.
I think Churchill was quite correct that the Battle of the Atlantic was the one front where Britain could really lose the war because they were so dependent on supplies, even food, coming from North America, that if that lifeline was cut, Britain would have been really in dire straits.
With the defeat of France, bases are built right on their coast, giving these vessels an even bigger theatre to disrupt the lifeline of Britain. Had aerial forces worked closely with these U-boats, or if a separate naval aviation wing was created, it would be a game-changer in Germany's war against Britain. Proof of this can be seen in the Focke-Wulf 200 Condor, an aircraft that, despite its limitations, is excellent in attacking English ships. With no more than a dozen planes, they successfully sink 85 merchant vessels and over 300,000 tons of shipping.
When the Germans started to deploy a fairly small number of the Focke-Wulf 200 Condors to attack Allied shipping, they were able to have really a devastating effect.
Also, had the new invention of a magnetic mine been dropped by Luftwaffe planes into the English Channel, its enemy could have been starved out of the war. This marks the first major failure of the Luftwaffe.
It was our common complaint of us, the little people, let's say, that there was no coordination whatsoever between the German Navy and the German Air Force.
With a stalemate on the Western Front, Germany decides to keep the British at bay and instead focus attention on their ally, the Soviet Union. Enacting a war plan known as Operation Barbarossa, some 3 million Nazi soldiers equipped with rifles, tanks and planes begin the biggest land assault in history. Using less than 3,000 aircraft, a force smaller than that utilized in the battle against France, Germany is miraculously able to push back Soviet forces to the suburbs of Moscow. The decision to launch Operation Barbarossa exposes the Luftwaffe to its second major failure: the lack of maintenance and repair on the ground. When a German aircraft is damaged, it is sent back to the fatherland for repair. When fighting a relatively short and tactical war against France, this particular system works fairly well. When fighting a long, drawn-out war of attrition against the communists, however, it proves to be a gigantic blunder. In the Soviet Union, with the fighting taking place far away from the major cities of Germany, the time it takes engineers to repair a damaged aircraft and have it sent back to the front is enormous. And by 1941, less than 30% of the Luftwaffe's airfields are operational, a fact that is almost inconceivable when taken into account that Germany is fighting a two-front struggle. As Field Marshal Erhard Milch would reflect after the war, the vertical organization in 4 territorial determined Luftflotte commands was grossly inadequate for launching a war well beyond the borders of the Third Reich. The attack of June 22, 1941 would in retrospect be a catastrophic mistake. For those like Goering, men who had never fought on the Eastern Front during the First World War, they would grossly underestimate the Soviet will and the industrial capacity of a regime thought to be so backwards by Hitler. Moving its factories far beyond the Ural Mountains, they are out of range of German bombers. The ghost of General Wefer comes back to haunt the Luftwaffe. After the Japanese attack on Pearl Harbor, Germany declares war against the United States. Before this decision is made, Hitler shrugs off any suggestion of a possible American threat in the form of an arsenal of democracy. In declaring war, Hitler foolishly adds yet another enemy to the Third Reich's list, one with a production capacity that is unparalleled. With two oceans separating America from the fighting, its people can go on producing without the threat of bombardment. Britain would have hauled the flag down long ago if it had not been for America's support, one field marshal said. With Germany by this time experiencing severe shortage of aluminium and copper, America is fully stocked of these and other vital raw materials. By 1944, the United States is able to churn out over 96,000 planes per year, one every 5 minutes, more than double that of the Germans. Before this catastrophic decision is made, it is important to note that by 1940, even Britain, with its shipping being torpedoed at an unprecedented rate, is outproducing Germany in aircraft. The British are able to improvise, and as a result produce outstanding planes like the de Havilland Mosquito, an aircraft made from plywood. In contrast, by 1941, with Nazi forces engaged in a two-front war, total production is just over 11,000 planes, a yearly increase of only 3,000 from when the war began. It is clear that the Third Reich's total output is only a fraction of what it could be.
One of the failures of the German Luftwaffe was their inability ever to work out a sane procurement and production process. Prototypes would be built and abandoned. They would be rebuilt and altered by Hitler's order and abandoned, and rebuilt a third time and perhaps put into production as an aircraft very, very different from what the original designers had intended.
This lack of planning and foresight can be attributed to the man who took control of Luftwaffe production in 1936, long before the war began. His name is Ernst Udet. An outstanding ace from the First World War, he is put in control by Goering, replacing Wilhelm Wimmer. His appointment to this powerful position marks the third, and possibly the greatest failure of the Luftwaffe.
Goering placed one of his World War I fighter ace buddies, Ernst Udet, in charge of technical developments. Udet really didn't know anything about this stuff.
Udet's forerunner, Wimmer, has been outstanding in overseeing the Luftwaffe's second-generation aircraft during the pre-war era, including the Me-109, the Junkers 87, and the Heinkel 111. With Udet as his replacement, however, the next line of aircraft is a far cry from their predecessors.
One of his hobby horses was dive bombers. He had seen, actually, in America, interestingly, between the wars, a demonstration of dive bombing, thought every German bomber should be made into a dive bomber, and then even ordered this new four-engine bomber, Heinkel 177, under development, to be made into a dive bomber. Well, Heinkel himself, who was, after all, an engineer who understood this, kept trying to talk him out of it, said this is ridiculous, but was overruled, and so they had to go back and strengthen the wings of the 177 to try to reduce drag so it could actually dive at high speeds. They tried mounting the engines in pairs instead of having four engines like you would normally think you would do on a bomber. They were mounted front and back in a single pod on each wing. This resulted in so much heat being generated that the engines were constantly overheating. So it really, I mean, it was a crazy idea, and it led directly to delays, and I guess you can really say the ultimate failure of Germany to field an effective four-engine bomber during the war.
The Heinkel 177, with its odd tandem engine arrangement and an insane requirement by Udet to dive bomb, makes this plane a complete disaster from start to finish. The aircraft becomes known as the dead racehorse, with only a handful ever getting the chance to fly.
The Heinkel 177 and the Me-210 go hand in hand as one of the Luftwaffe's major disasters.
The Messerschmitt 210, a replacement for the Me-110, is full of problems that are never ratified.
When he came up with his Messerschmitt 210, The RLF said, oh yes, that's very good. Let's immediately, we'll order 10,000. Or whatever it was. But they went into mass production and the thing had hardly flown. It was a complete and utter disaster for Messerschmitt, which he'd never lived down. And they had to convert a lot of the built ME-210s into ME-410s by taking the aeroplanes to pieces again and reassembling them with new parts to turn it into a flyable and operational machine.
As one aircraft representative is overheard saying, everything turns to dust in Udet's hands. Only one aircraft, the Focke-Wulf 190, is considered a success under his watch. A reluctance to make the hard decisions also proves costly, as resources are diverted to projects that are simply unfeasible during wartime. By 1941, the need is for long-range strategic bombers, with America producing the B-17 Flying Fortress and the British reworking the Avro Manchester into the four-engine Avro Lancaster. Germany, in contrast, falls dramatically behind the Allies in producing four-engine bombers. Udet, with all his failures, commits suicide in 1941, leaving the Luftwaffe in shambles. With a Soviet victory at Stalingrad, German forces are pushed back, marking the beginning of the end. And as American and British bombers begin destroying German factories and city centers from the sky, the philosophy that General Weber endorsed years ago is coming true. Strategic bombing is proving vital in weakening the German war machine. Under the command of Field Marshal Erhard Milch, production is able to climb to 25,000 planes a year, a respectable increase, but nothing compared to what the Allies are able to produce.
U.S. procurement policies, which become a giant bureaucracy, embodied in the War Department and soon thereafter, World War II, embodied in the Pentagon. The Germans were simply not able to compete on that level.
In 1944, Germany is being outmaneuvered in the realm of aircraft by the rate of over 4 to 1. At this point, there is simply no way to compete with the United States or the Soviet Union. While much is written by historians about Allied coordination in resources and materials, little can be found about Germany's willingness to use its own allies' means of production to their advantage. This is yet another failure of the German Luftwaffe. Without a common goal and being on different sides of the world, the Empire of Japan cannot be considered Germany's biggest ally. Its most powerful friend during the war is instead the Italians. Unfortunately, with their own air force in shambles, the Nazis are reluctant to give them the licenses and the engines to build German planes on Italian soil. This proves to be a pivotal mistake, as Italy could have tripled aircraft production with German assistance, producing possibly 30,000 planes during the war. Also, Italian factories would have been out of bombing range for the Allies during the year 1942 and might have changed the outcome in the Mediterranean. Germany's other allies, Romania, Hungary, and Finland, are all capable of making aircraft, but lack the knowledge and resources that the fatherland can provide. Had these nations been granted licenses to build Nazi aircraft on their own soil, there was a good chance that this coalition might have tipped the scale in favor of Germany during its pivotal battle against the Soviets during 1941. The decision not to fully utilize the resources of these nations can be attributed to Germany's desire to be the dominant power. There is widespread resentment against the Italians by top Nazi leaders who see them as merely riding off the coattails of German success.
Our feeling always was, with the experience of the First World War already, we wish the Italians were on the other side.
People like Hermann Goering see these smaller countries as the providers of natural resources, with the fatherland supplying the finished products. This marks another tragic failure of the Luftwaffe. In early 1944, Germany unveils the Messerschmitt 262, a revolutionary jet plane that can hopefully take down the flying fortresses and mosquitoes that are destroying their cities.
Later on, of course, they produced the world's first production model, general use jet aircraft in the form of the Messerschmitt 262, the Me 262. The Me-262 as a pure fighter was an amazing sight to see, and in fact, anyone looking at it today is still struck by the modern and sleek lines.
Now, the Me-262 was, in my opinion, I've stated this many times, the most formidable aircraft of World War II.
The Me-262 is years ahead of its time, symbolizing the fatherland's creativity and innovation. In many ways, however, the Me-262 also symbolizes Nazi indecision.
Unfortunately, the Me-262 got caught in a very, very arcane and difficult procurement process within Germany, wherein basic designs were put forward by competent engineers. They were then changed by upper echelons within the Luftwaffe, and of course they had to pass the Hitler test. And no aircraft passed the Hitler test without being significantly modified. The Me-262 is no exception.
After Professor Messerschmitt tells Hitler that the aircraft can carry up to 1,000 kilograms of bombs, Field Marshal Milch, in a fit of rage, tells the Führer that even the smallest infant can see that the 262 is a fighter, not a bomber. After months of wavering, the plane goes ahead as a fighter-bomber, taking the sting out of what could have been a ferocious punch. They may possess this wonder weapon, but have few men that can fly it. This becomes the Luftwaffe's final failure, its pilots' lack of training. During its heyday, Germany's finest were given approximately 250 hours of flight time before being sent out to face their enemy, considerably more than the British. And with the Second World War going exceedingly well during 1940 and 1941, the Luftwaffe arrogantly minimizes its training program, figuring that the war will soon be over. By 1942, as the tide begins turning, German pilots are given less than 200 hours of practice flying, while Allied pilots are given over 300. With the war turning against them, shortcuts are made to churn out every single pilot possible. Despite this augmentation, by 1944 the average training time drops to just under 100 hours. In some cases, just a quarter of what P-51 Mustang and P-47 Thunderbolt pilots were given. With air superiority lost over German soil, it becomes a turkey shoot for American and British aviators as they begin gunning down Me-109s and Focke-Wulf 190s with ease.
At D-Day, in the final planning, the head of Allied Tactical Aviation was asked, well, what are we going to do about the German fighters? He said there aren't going to be any German fighters over the landing beaches. And he was essentially right, because they'd been wiped out by that.
The decision not to build a pilot training infrastructure like its enemies causes the Luftwaffe to run desperately short on experienced men. So by the time planes like the Me-262, the Arado 234 jet bomber, the Me-163, a rocket-powered interceptor, the Dornier 335 Arrow, the fastest piston-engine plane of the Second World War, and all the other revolutionary aircraft that could have been the difference-maker on both fronts, it is a case of too little, too late. The defeat of the Luftwaffe can be attributed to its lack of direction. With the war going in Germany's favor, Hitler, Goering, and Udet were blinded by a false optimism. The tactical war doctrine that they favored initially was being replaced by a long, drawn-out strategic war that they were ill-prepared for. The arrogant nature in which they brushed off the industrial power of the United States and the Soviet Union. The mismanagement of their own country's aircraft industry on a grand scale, and the lack of infrastructure, production, and training during the Second World War's most decisive years would cause the Luftwaffe to write.
Every aircraft has a story that deserves to be told. Don't let these legends fade into the past. Like this video and subscribe to our channel and help us keep aviation history alive.
In the autumn of 1944, the south of England was introduced to a terrifying new weapon, known locally as the Flying Gas Works. The rest of the nation called it the V-2, but in its German birthplace it was the A4 rocket. Fired from ordinary city streets and quiet wooded avenues in Holland, these projectiles struck London with zero warning.